This is Dr.BDY Sunil, Associate Professor, Mechanical Engineering Department, Institute of Aeronautical Engineering, Hyderabad. In this session, we will be solving few problems on equilibrium conditions, supports and support reactions. Let us solve a problem on state of equilibrium. The problem given is, determine the horizontal force P to be applied to the block of weight 1500 newtons to hold it in position on a smooth inclined plane AB, which makes an angle of 30 degrees with the horizontal. The very first thing that we have to do while solving a problem is to draw a free body diagram of the given system. In the given system, there is a force P that is being acted upon the body horizontally and the weight of the body acting vertically downwards. And there is a plain frictionless support at an inclination of 30 degrees to the horizon. Now, for drawing a free body diagram, we have to remove the supports and mention the reactions on the body and in the direction towards the body. Also, we have to represent all the forces in the system as it is. So, the free body diagram of the given system is as represented here. So, in the free body diagram of the given system, first the given body is drawn, which is the block as it is in respect to the position. Force P is represented at the point and direction as it is. And the weight of the body 1500 newtons is shown vertically downwards, which will act from the center of the body. Always, the weight of the given object should be represented from the center of the body and in vertically downward direction. Even though the body is in any orientation, that is horizontal or inclined, the weight must be represented vertically downwards. After removing the support of inclined plane, the reaction R is given normal to the support and towards the body center. This 30-degree angle is obtained by simple triangle angles principle, considering the alternate angles and sum of the angles of the triangle and so on. Also, the inclined reaction force is divided into components Rx and Ry in mutually perpendicular directions, and their values are R sin 30 degrees in horizontal direction and R cos 30 degrees in vertical direction as per trigonometric ratios. This is the free body diagram of the given system. Now we can solve the problem by using conditions of equilibrium. After completing the free body diagram, first we will do the sum of the horizontal components equal to 0. That is, sigma fx is equal to 0. In the system given, there are two horizontal forces. One is horizontal force P and other is the horizontal component force of R, that is Rx. Hence, P plus minus R sin 30 degrees is equal to 0. We have taken negative symbol because the component is in negative axis direction. So, P is equal to R sin 30 degrees. Now, the sum of vertical components is equal to sigma Fy is equal to 0. In the system given, there are two vertical forces. One is the weight of the block and the other is the vertical component of R, that is Ry. Hence, minus 1500 plus R cos 30 degrees is equal to 0. Solving this, we get R is equal to 1732.06 Newton. Substituting this value in equation P, we get P is equal to 1732.06 into sin 30. That is equal to 866.03 Newton. Thus, the force of 866.03 Newton is to be applied horizontally onto the block to hold it in position. Let us solve a problem on connected bodies. If in a system, two or more bodies are in contact with each other by any means, say a string connected to two bodies, or a bar connecting two bodies, or even two bodies in direct contact with their surfaces, then these systems are termed as connected body systems. The procedure we use here to solve the problem on connected body system is to apply the equilibrium conditions to individual bodies to find the reactions and unknown forces on the body and solve the equations we obtain. The problem given is two rollers of diameters 30 mm and 60 mm weighing 40 newtons and 160 newtons respectively are placed as shown in figure. Assuming all contact surfaces are smooth, find the reactions at A, B, and C. In the system of connected bodies given, there are two rollers in contact with each other. Here, both the rollers will apply a reaction force on each other which is in equal magnitude. That is, if RD is the reaction force at the contact point of D, then at the point of contact is 160 kilonewton roller will apply RD reaction force on 40 kilonewton roller, and the 40 kilonewton roller will apply RD reaction force on 160 kilonewton roller. And when we draw the free body diagram, we have to represent the reaction force RD on both the rollers in the direction towards their center. Now let us draw the free body diagram. In this free body diagram, we have removed the wall supports and represented the reactions at the contact points of A and C normal to the surface and towards the body center, which are horizontal. We have also removed the inclined bottom surface support and represented the reaction at the contact point B, normal to the surface and towards the center of the body. For 40 kilonewton roller, there is no contact of the roller in the inclined surface. Hence, we have not represented any reaction force here. With the clue given by the inclination of the bottom inclined surface of 45 degrees, we can represent the inclination of RB as 45 degrees to the horizontal. But for RD, we have to find the inclination. Let us find it first. Let the horizontal distance of the centers of rollers be x and inclination of the line joining the centers be alpha. Now, for finding x is equal to 72 minus 30 plus 15, which gives 27 millimeter, where 30 is the left side portion of the roller from the center of the big roller and 15 is the right side portion of the small roller. So, if we remove these parts from the total horizontal distance of 72 millimeters, we will be getting the linear distance between the two centers of the rollers, which is 27 millimeters as calculated. Now, for finding the inclination, we can apply trigonometric ratio to the triangle formed here. That is, cos alpha is equal to x by 30 plus 15, which are the radii of the rollers. That is equal to 27 by 45. Solving this, we get the inclination. Alpha is equal to 53.13 degrees. Now, let us apply equilibrium conditions to 40 kilonewton roller first. So, applying sigma Fy is equal to 0 implies minus 40 as the force is acting downwards plus Rd sine 53.13 degrees is equal to 0. Solving this, we get Rd is equal to 50 kilonewton. Also, sigma Fx is equal to 0 implies minus Rc as the force is in negative direction plus Rd cos 53.13 degrees is equal to 0. Solving this, we get Rc is equal to 30 kilonewtons. Now, let us apply equilibrium conditions to 160 kilonewton roller. So, applying sigma Fy is equal to 0 implies minus 160 as the force is acting downwards minus Rd sine 53.13 degrees as the vertical component is acting downwards plus Rb cos 45 degrees is equal to 0. Solving this, we get Rb is equal to 282.89 kilonewton. Also, sigma Fx is equal to 0 implies Ra minus Rd cos 53.13 degrees as the component is acting in negative direction minus Rb sin 45 degrees as the component is acting in negative direction is equal to 0. Solving this, we get Ra is equal to 230 kilonewtons. Thus, the reactions at A, B and C are 230 kilonewtons, 282.89 kilonewtons and 30 kilonewtons respectively. In this way, by drawing the free body diagrams of individual bodies in a connected body system, we can obtain the reactions and other unknown forces. Thus, the problems will be solved. This concludes the session. Thank you.
Like, share and subscribe. hit the bell icon for more updates.